Hi students, today we start our next topic in the chapter of solution, and that topic is the solubility of gas in liquid. In the last class we have briefly discussed about the solubility of solid in the liquid and how the solubility of solid in liquid is affected by using the different type of factor, and these factors are the nature of the solute, temperature. For today we are discussing about what is the solubility of gas in liquid. When the gases are passes through the liquid solvent, it dissolve in it. Initially we found that these gases are dissolved in the liquid solvent and the concentration of the solution is gradually increases, and after some time a state of equilibrium is attained, and at that particular time that solution is named as the saturated solution. So students, what is the solubility of gas in a liquid? How can we define the solubility of gas in a liquid? The solubility of a gas in a liquid is defined as the number of moles of gases that can dissolve 1 liter of the solvent at the given temperature, or in other words it can also be defined as the number of mole fraction of the gases that can be dissolved in 1 liter of the solvent. Then the solubility of gases in liquid. The solubility of gases is generally expressed either in the term of number of mole of a gas that can dissolve per liter of solvent at the given condition, or more conveniently in term of mole fraction of the gas. Next is what are the factors affecting the solubility of gas, in which the first is the nature of the gas and the nature of the solvent. Second is the effect of temperature and effect of the pressure. So our first factor is the nature of the gas and the nature of the solvent. Same gas dissolve to different extent in different solvent, and different gases dissolve to different extent in same solvent. And the solubility of the gas in different solvent or the solubility of different gas in the same solvent is explained by giving one example. Dear students, we generally know that the gases like hydrogen, oxygen and nitrogen gases, these gases are the non-polar gases, and these gases are showing very less solubility in the water, whereas the gases like carbon dioxide, sulfur dioxide and ammonia, these gases has very high solubility in the water, and their high solubility in the water is due to their tendency to show chemical reaction with the water molecules. I am giving you the reactions. Just for example, when this carbon dioxide is reacted with water, it gives HCO3 plus H plus carbonic acid. Then when this sulfur dioxide is reacted with water, it gives HSO3 negative plus H plus. Similarly, the ammonia NH3 also reacted with water, and it gives the ammonium ion along with the liberation of hydroxy anion. So the gases which has showing its tendency to combine with the water, they show its solubility in the water. The next thing is temperature. When a gas is dissolved in a liquid solvent, we observe that in the gaseous molecule, the random movement of the gaseous molecules are continuously decreases. It means there is a decrease in the net enthalpy change of the solution is observed. It means the delta H sol means the total net change enthalpy in the dissolution process comes in the negative sign. It means the dissolution of a gas in a liquid is an exothermic type of reaction, and when any reaction is an exothermic reaction, in this condition when we increase the temperature, the increase in the temperature proceed in the backward direction. It means it decreases the solubility of gas in a liquid, and when we are increasing the temperature, the gaseous molecules are escaped out of the gaseous solution and they are removed out of it. Another factor is pressure. Unlike solid, the gases are compressible. So when we are dissolving the gas in a liquid solvent and during their dissolution, when we apply a high pressure, the high pressure increases the solubility of gas in a liquid. So these three are the important factors which are affecting the solubility of gas in a liquid. Then students, our next topic is Henry's law. Henry's law states that the solubility of a gas at the given temperature is directly proportional to the pressure at which it is dissolved. So, XB is the mole fraction of the gaseous molecules which are undergoing to dissolve in the liquid solvent, and this XB represent the solubility of the gas. And in this case, the P, that P is the pressure at which the gas is dissolved in the solution. So according to Henry law, this solubility of the gas is directly proportional to the pressure at which it is dissolved, or in other words we can represent it, the pressure is directly proportional to the mole fraction of the gaseous molecule. And in any condition, when we remove the proportionality, a constant is added, that is the KH into XB. This KH is a constant of proportionality which is named as the Henry law constant. Next is, what are the important characteristics of Henry law? The important characteristics of Henry laws are, KH is a function of nature of the gas. Higher the value of KH at the given pressure, lower is the solubility of gas in the liquid. The KH value of a gas is different in different solvent and it increases with increase in the temperature. The knowledge of KH value of a gas at given temperature help us in calculation of solubility at that temperature. As the temperature is increased, the solubility of gas decreases. This implies that higher the value of KH of a gas, lower will be its solubility and vice versa. So after that, what are the basic application of Henry law? The basic application of Henry law are in three cases. The first is in the production of carbonated beverages, for climbers or people at high altitude, and in deep sea diving. Let me explain the application of Henry law. The first application is in the production of carbonated beverages. In the cold food and soft drinks as well as in the beverages, there is a carbon dioxide is dissolved, and during the manufacture of these beverages, the carbon dioxide gas is dissolved at very high pressure to ensure its high solubility in these drinks for climbers or the people living at high altitude. Dear students, as we know that when we are approaching at high altitude, the pressure of oxygen in the atmosphere is gradually decreases. So, the people who are living at the high altitude or the mountain climbers, these mountain climbers carry the oxygen cylinder because at the high altitude, the pressure of oxygen is very low. So, in such condition, the peoples who are living at that places are suffering from a condition. That condition is named as the anoxia, and that condition arises in the body of the people due to the lower pressure of oxygen in the blood or in the tissue of the people. And in this condition, the people will become very weak and they reduces their mental ability. The third condition, the third application of the Henry law is in the deep sea diving. The scuba divers carry a breathing apparatus that contain the compressed air. These scuba divers will suffer from a painful condition that is named as the bends when they come to the surface, and this painful condition arises in the body of a scuba diver is due to the depression of gases dissolved in their blood when they are breathing at high pressure under the water. So students, these are the basic application of the Henry law. The Henry law is also applicable for the functioning of our lungs. Now our next topic is the vapor pressure of liquid solution. In this chapter, we shall limit our discussion only to the vapor pressure of binary solution of liquid in liquid type and solid in liquid type. We first discuss the topic, what is the vapor pressure of liquid? What is the vapor pressure of liquid? And that concept can be clearly understood by taking an example. Suppose when the liquid solvent is taken in a beaker and that beaker is covered from the top, a part of that liquid get evaporate and it fill the space which is available to them. Initially it is found that the number of molecules in the vapor state are gradually increases and some of the vapor molecules get strike with the surface of the liquid and get condensed there. After some time, a state of equilibrium is attained between the vapor phase and the liquid phase. At that particular equilibrium state, that pressure which is exerted by the vapor over the liquid surface in equilibrium with the liquid solution at the given temperature is named as the vapor pressure of the liquid. So students, the vapor pressure can also be directly proportional to, this vapor pressure is also directly proportional to the escaping tendency of the liquid. If the escaping tendency of the liquid is more, it means more number of molecules are converted in the form of vapor and after some time it exerts a pressure over the liquid surface and that pressure is named as the vapor pressure. So the vapor pressure of a liquid solution is the pressure exerted by vapor in equilibrium with the liquid solution at a particular temperature is called vapor pressure, and the vapor pressure is directly proportional to the escaping tendency. Next is the vapor pressure of solution of solid in liquid. When a non-volatile solute like sucrose, glucose or sodium chloride is dissolved in volatile solvent, in this case the vapor pressure in the solution is only due to the component of the solvent because the solute is non-volatile in the nature, and when a non-volatile solute is added in the solvent, it is observed that the vapor pressure of the solution is lower than the vapor pressure of the pure solvent. This lowering in the vapor pressure of the solution can be explained on the basis of the surface area which is available for the evaporation. Dear students, it can be explained. Here we are taking the pure solvent and this is the area which is available for the evaporation of the liquid solvent, and here we are adding the solute in the solvent, and in this case it is observed that some of the area of the liquid surface are get occupied by the solvent molecules. So the decrease in the vapor pressure can be explained on the basis of the area which is available for the evaporation. In this case, this is the vapor pressure of the pure solvent. In this case, there is a complete area is available for the evaporation of the solvent, and in this case, when the area is more, there is a greater tendency of the molecule is observed to convert in the form of vapor. Whereas when a non-volatile solute is added in a volatile solvent, in this case, some of the places of the volatile solvents are get occupied by non-volatile solute. It means in this case, the surface area which is available for the evaporation is get reduced, or in other words we can say that the number of molecules which are having the tendency to escape into the vapor state are get decreases, and this is named as the lowering of vapor pressure. Next is the vapor pressure of liquid in liquid solution. When two miscible volatile liquids are mixed together to form a solution, in this case the vapor pressure of the solution is the sum of vapor pressure of the individual component, that is in accordance with the Dalton's law of partial pressure, that is P total. The total vapor pressure is equal to the vapor pressure due to the component 1 and vapor pressure due to the component 2. It means the total vapor pressure when two volatile liquids are mixed together, in this case in the solution the vapor pressure is due to both the component 1 and the component 2, because both the component has tendency to escape into the vapor state, and this is in accordance with the Dalton's law of partial pressure, which is the sum of total vapor pressure is the sum of vapor pressure of the individual component. After that, it is very important to note down that what are the factors which are affecting the vapor pressure of a liquid. The vapor pressure of a liquid are generally varies on different liquids basis. The first factor is the nature of the liquid. What is the nature? Nature means if in a liquid there is a weak intermolecular forces are present, it means that particular liquid is more volatile as compared to another, because when there is a weak intermolecular forces are present in that liquid, there is a greater tendency of evaporation is observed, and they are showing a great tendency to escape in the vapor form, and consequently they exert a more vapor pressure over the solution. Next is the next factor is temperature. When we are increasing the temperature of solution, in this case increasing the temperature increases the kinetic energy of the molecule, and which in turn increases its tendency to escape in the vapor state. It means the more the temperature, more is the vapor pressure is observed. Dear students, after that the next is RAOULT'S law. What is RAOULT'S law? The Raoult is a chemist. He carried out a number of experiments on the binary solution to study the vapor pressure, and on his study he studied on two things. The first is the Raoult's law for solid in liquid, and another is liquid in liquid. According to Raoult's law, when a non-volatile solute is dissolved in a volatile solvent, the vapor pressure of the solution is directly proportional to the mole fraction of the solvent only. It means the vapor pressure of solution is equal to, the vapor pressure of the solution is equal to the vapor pressure of solvent, because in this case the solute is non-volatile and the vapor pressure of the solvent is represented by Pa, and that vapor pressure of the solvent is directly proportional to the mole fraction of the solvent which is present in the solution. That is, the Pa is directly proportional to Xa, and when we remove the proportionality, a constant is added, that is the Pa naught Xa. That Pa naught is the vapor pressure of the component in its pure state. This is the Raoult's law for a solution in which a non-volatile solute is dissolved in a liquid solvent. Another condition is Raoult's law. This is the first condition. Second condition is the Raoult's law for a binary solution containing two miscible volatile liquids, that is the liquid in liquid type of solution. When a liquid is dissolved in a liquid solvent, just for example, when we take the two components are A and B. These two components are dissolved together to form the solution. In this case, if Xa is the mole fraction of the component A and Xb is the mole fraction of the component B, and in this condition if Pa is the partial vapor pressure of the component A and Pb is the partial vapor pressure of the component B, then according to Raoult's law, in this condition the Raoult's law states that for a solution containing two or more miscible volatile liquids, the vapor pressure of each component is directly proportional to its mole fraction. Means the Pa is directly proportional to the mole fraction. The vapor pressure of the component A is directly proportional to the mole fraction of the component A. So when we remove the proportionality, the Pa is equal to Pa naught Xa. Similarly, for the component B also it can be written as the Pb is directly proportional to Xb and Pb is equal to Pb naught Xb. Here the Pa naught is the vapor pressure of the component in pure state, it is a constant value. Pb naught is the vapor pressure of the component B in the pure state. So students, according to Raoult's law, when we plot PA against XA. When we plot, here it is represented vapor pressure on this axis, and on this axis we represent the mole fraction. Here is the XA is equal to 0 and XA, the mole fraction of the component A is 1. Here the XB is equal to 1 and XB is equal to 0. So according to Raoult's law, when we plot a graph between the PA and XA, in this condition we found a straight line passing through the PA naught. This PA, at this PA naught, the XA is equal to 1. It means in this case the solution, the vapor pressure in the solution is only due to the component A. Similarly, for the component B, when we plot XB against PB, same we get a straight line which passes through the PB naught, and at that PB naught the XB, the mole fraction of the component B, is equal to 1. So according to Dalton's law, the total vapor pressure of the solution is the sum of, when we join these two lines, we get P total, that is the total vapor pressure in the solution, which is equal to PA plus PB. That is the sum of vapor pressure of the individual components. After that, it means according to Dalton's law, the P is equal to PA plus PB. According to Raoult's law, this PA is equal to PA naught XA plus PB naught XB. So this XA in a solution, since XA plus XB is equal to 1, so the PA naught we can place at the place of XA 1 minus XB plus PB naught XB. Similarly, PA naught, when we multiply this with 1, PA naught minus PA naught XB plus PB naught XB. In these two cases, the XB is common, so we get PB naught minus PA naught XB plus PA naught. That is the equation to calculate the total vapor pressure of the solution. Similarly, when at the place of XB, when we place 1 minus XA, then we get P is equal to PA naught minus PB naught XA plus PA naught. These two equations, these are the two equations which are used to calculate the total vapor pressure of the solution when two volatile liquids are mixed. From these two equations, dear students, it is clear that this PB naught and PA naught are the constant term. It means the vapor pressure of the solution is a linear function of the mole fraction of the component. The mole fraction of the component A and the component B. This is the in accordance with the Raoult's law. The vapor pressure of solution of solid in liquid and the Raoult's law can be stated when the non-volatile solute is dissolved in it. If a non-volatile solute is added to a solvent in a solution, the number of solvent molecule escaping from the surface correspondingly reduced. The vapor pressure is also reduced. Thus the Raoult's law in such case states that the vapor pressure of the solution containing non-volatile solute is directly proportional to mole fraction. Next is the vapor pressure of liquid solution and Raoult's law. The Raoult's law for volatile solute, it states that for a solution of volatile liquid, the partial vapor pressure of each component in the solution is directly proportional to its mole fraction. The next is, it is observed that the Raoult's law is a special case of Henry law. Dear students, according to Raoult's law, the partial vapor pressure of the volatile component is equal to the vapor pressure of the component in the pure state into the mole fraction of the volatile component. Similarly, when the gases are dissolved in the liquid solvent and the gases are volatile in the nature, so the solubility of gas in the liquid is governed by Henry law. And according to Henry law, the pressure at which the gas is dissolved in the liquid solvent is equal to the Henry law constant into the mole fraction of the gas which is dissolved in the liquid solvent. When we compare these two equations, the equation 1 and equation 2, it is clear that the pressure of the volatile component, here the pressure of the volatile component A, and this is the pressure of the gases. This pressure of the volatile component is directly proportional to the mole fraction of that component, and the only difference in these two equations is of the proportionality constant. In the case of Raoult's law, the proportionality constant is the vapor pressure of the component in the pure state, where in the case of Henry law, the proportionality constant is a Henry law constant. So, these two equations become identical when the Henry law constant is equal to the vapor pressure of the volatile component in the pure state. So, students, this implies that the Raoult's law is an special case of Henry law when the Henry law constant is equal to the vapor pressure of the component in the pure state. After that, we come on another topic, that is the ideal and non-ideal solution. Ideal solution. In the case of binary solution, the liquid solutions are further classified into ideal solution and non-ideal solution. Ideal solution means the solution which obey the Raoult's law over the entire range of concentration and temperature. Students, actually there is no solution which strictly behave as an ideal solution, but the solution in which the solute and solvent interaction is nearly same as the solute-solvent interaction. Those type of solution nearly behave as a ideal solution. In the case of ideal solution, it is also observed that there is neither any change in the volume nor any change in the enthalpy. So, the ideal solutions are generally governed by the three conditions. The first condition is that it obeys the Raoult's law, that is PA is equal to PA naught XA and PB is equal to PB naught XB. The first condition is that the ideal solution obey the Raoult's law, and the second condition is, this is the first condition, and after that the second condition is that delta V mixing is equal to 0. It means when we are mixing a particular amount of liquid solvent in a particular amount of liquid solute, in this case there is no change in the volume is observed. And the third condition is delta H mixing is also equal to 0. It means there is no change in the enthalpy is observed during the dissolution of solute in the solvent. These three are the conditions for the ideal solution. Another is non-ideal solution. So, the another type is non-ideal solution. The non-ideal solutions are generally defined as the solution which does not obey the Raoult's law over the entire range of concentration and temperature. The first one is the non-ideal solution showing the positive deviation, and the second one is the non-ideal solution showing the negative deviation. The three conditions for non-ideal solution showing the positive deviation is, for the positive deviation, it does not obey the Raoult's law. It means the PA is greater than PA naught XA, that is the vapor pressure is greater than this value, means it does not obey the Raoult's law, and PB is also greater than PB naught and XB. Second condition is delta V mixing is greater than 0. When the non-ideal solution is showing the positive deviation, delta V mixing is also is equal to 0. It means there is an increase in the volume is obtained when a solute is added in a solvent. And the third condition is delta H mixing is also greater than 0. In the case of non-ideal solution showing the negative deviation, the three condition is the PA is less than PA naught XA, the PB is less than PB naught XB. This is the first condition, because in the case of non-ideal solution, the PA, the vapor pressure is not is equal to the PA naught and XA, means it does not follow the Raoult's law. And the second condition is delta V mixing is less than 0. The volume is less than the actual volume which is added to form the solution. Third is delta H mix is also less than 0. Now students, let we understand this, the non-ideal solution showing the positive and negative deviation with the help of this graph. This is the graph which I have already drawn in the case of Raoult's law. In this condition, non-ideal solution showing the positive deviation. This line is in accordance with the Raoult's law. This line is in accordance, it follow the Raoult's law. It means the partial vapor pressure of the component is directly proportional to the mole fraction. But in this case, the dotted lines show that this is the plot, this is the line which show the non-ideal solution showing the positive deviation, because in this case there is increase in the vapor pressure is obtained, and this increase in the vapor pressure is basically understood on the basis of the interaction between the solute-solute, solvent-solvent and solute-solvent interaction. The solution which are showing the non-ideal solution with positive deviation, in this case there is a weak interactive forces are operated between the solute-solvent as compared to the solute-solute and solvent-solvent. And when the interaction between the solute and solvent is weak, it means in this case the molecule has greater tendency to escape into the vapor form. And when they have more tendency to escape in the vapor form, it means its vapor pressure is more than that expected in the case of Raoult's law. Similarly, the non-ideal solution showing the negative deviation, in this case the line is obtained like that. In this case, this line is down. This is the non-ideal solution showing the negative deviation. The vapor pressure is lower than that expected in the case of Raoult's law. And the reason behind that is, in this case the solute-solvent interaction is more than the solute-solute and solvent-solvent interaction. And when the interaction between the solute and solvents are more, it means there is a less number of molecules are now available to escape in the form of vapor, and consequently there is a decrease in the vapor pressure is observed in the case of non-ideal solution showing the negative deviation. I would like to show you some example of the non-ideal solution showing the positive deviation. These are the water and methanol, water and ethanol. Some of the example of the non-ideal solution showing the negative deviations are water and HCl, water and hydrochloric acid. Okay students, at last I hope that all of you have clearly understand this concept of vapor pressure, Raoult's law, Henry law and the non-ideal and ideal solution. So students, I request you all that all of you must go through this chapter and try to understand all these concepts, and if you feel any difficulty during these topics, then you please concern to your concerned subject teacher.